What you see on the title slide is the environment where our manipulation problem takes place. So we'll be talking about this. It's a little bit of something for everyone. One of my favorite things about robotics is we need hardware, software, motion planning, control, computer vision, machine learning, manufacturing operations. We've got it all. So here's a teaser at the start. The task is to put inventory onto these bookshelves. And the bookshelves are made of a really heavy fabric, kind of a canvas, so it's a little bit flexible. We've got these mesh elastic bands that sit in front of those bookshelves, protecting the items from falling out. You can see there's a diversity of items. It's basically anything you could buy on Amazon.com that's less than 20 pounds, less than 24 inches. They get stored randomly, so it's not like it's all iPhones in one shelf. It could be a teddy bear next to an iPhone, next to a bowling ball, next to a light bulb. So Mark mentioned this. I did have a whole lot of fun my first 15 years as a roboticist, first here and then at JPL. I won't be talking about that today. I did do a Robotics Institute seminar at Carnegie Mellon in the fall of 2019. And that's right when I was making the transition, and so I actually remembered everything cool we were doing about ice climbing and asteroid gripping. And if you're really interested in that, I encourage you to look it up on YouTube. So this is an Amazon warehouse. I want to talk you through the sort of overall process, and then we'll zoom in on the manipulation problem that we're trying to solve. Trucks basically show up, and this is the inventory arrives step. We unload all of those items that are not yet for sale. We store them on those yellow bookshelves. We break them down, singulate them, so it's a one-by-one process of storing them randomly on those bookshelves. At that point, they're for sale on the website. And when a customer orders one of those items, we pick it off of that same bookshelf, try and accumulate it with any other things that you've ordered within the last 6 to 12 hours, pack those into the smallest and greenest shipping container that we can get you your order in, and sometimes that's no shipping container at all, right? I order a lot of diapers these days. It just comes with a shipping label on the diaper box. Once those packages are sealed, we do another sortation step to make sure everything coming to Stanford University is in one truck and everything going to Menlo Park is in a different truck, and then those trucks go out into the network. One thing to talk about is there's a big supply chain that exists before this with ports and boats and factories and inbound cross docks, and there's a big distribution network that happens after this building, which is delivery stations, third-party carriers like FedEx and UPS, further sortation centers. What you see here is just how many of these bookshelves there are. 60,000 of them in a given fulfillment center. There's 25 million items that would sit on those bookshelves. We process, on good days, over 1 million items in a single day. So it is a large-scale problem. With that scale comes both opportunity and challenges. So something that's a 1 in a million occurrence is a 10 or 20 times a day thing at Amazon. So these edge cases, the reliability, your ability to handle those things quickly and efficiently becomes really important. On the opportunity side, if you want to retrain a new model, we have massive amounts of data, right? So we have a package sorting robot called Robin that's now done something like 2 or 3 billion picks. And we have the kinematics and the trajectories for all 2 or 3 billion of those picks. And in fact, we just published a big data set to make that available to the community so that we could try and analyze and leverage that data. There's also, because of this scale, a tremendous opportunity to have a big impact, right? So if you can deliver something, it's going to go out and it's going to change the business pretty substantially. So let's zoom in here on Stow. This is what I'll be talking about. This is what we call that step of putting the items onto the bookshelf. You see a Kiva robot. That's what these guys here are that are moving those bookshelves around. Let's see if we can get that to play again. It comes to a person, so rather than a person walking down long aisles with a shopping cart, these robots are now bringing the bookshelves to the people. They will scan an item and then place it onto that shelf. I think I've got another video, yeah. And one of the favorite inventions Amazon came up with a few years ago for me is she'll scan the item itself, so we get a barcode read here. But once she places it into the bin, there's no subsequent scan. There's a machine learning model. It's using a couple of cameras that watches where the person's hand goes into the bin and automatically transfers that inventory into the appropriate shelf. And that's deployed widely at scale, so it saves a couple of seconds on each of these stows, and it also makes it way more ergonomically friendly. You don't have to carry a barcode scanner with you when you're doing this task. Other things you might observe when you're watching this is the workspace. So we need a ladder to get up to the top shelves. You've got to crouch down to get down to the bottom shelves. We really want these warehouses to be as dense as possible. When you're buying a 1 million square foot building outside of Tokyo or New York City or San Francisco, the real estate costs are quite expensive, and so density is really important to keeping the prices low for our customers. You'll also notice she's doing some decision making here. So she's in her head figuring out which item will fit in which bin and how to make space in that bin and when to kick that shelf out and get a new one in that has more opportunities. So it's this kind of matching game that you need to do. And then the manipulation tasks themselves, right? So dealing with those elastic bands is not trivial. Making sure that item will fit, especially if it's kind of a dense fit. As we're getting ready for the Christmas season, the holiday season, these things are getting as full to the gills as we can get them. And so sometimes it's pretty forceful to get stuff to fit in there. And you've got to think about whether you're going to damage the item. If it's a box of batteries, you can probably use a lot of strength. And if it's an iPhone, maybe you want to be a little more careful. So if we think about this from a robotics perspective, it's kind of these steps. You perceive the shelf, decide what goes where. You open those elastic bands, grasp the item you're going to stow, do this pre-manipulation inside the bin to get the space you need to stow that item, and then place the item onto the shelf. So we'll get pictures of the state of those shelves, but we also have metadata on all the other items that are already on that shelf, including properties like their dimensions, the weight. We track things like whether they're compressible or not, whether they're bagged or not, whether they're fragile, liquid, lithium batteries, that kind of stuff. We need to open those elastic bands. So here you see a 2-jaw version. Grasp the item. In this case, one of the simplifications we were able to do is feed the item into the hand using a conveyor. So there's not a lot of grasp planning. That was something we were able to get away with. We make space in the bin using a pretty simple manipulator. It's a piece of sheet metal that can extend in and out. And then we stow the item. And here, these are actually conveyor belts that are part of our gripper. And so we don't have to put the entire gripper into the bin, which takes up a lot of space. We can kind of feed that item in. The things we care about is how fast can you go? We're talking about hundreds of units per hour, so you're 10-ish seconds is a good rule of thumb to do this entire task. Eligibility, this is material to be handled. So what kind of items can you deal with? I like to call this a partial credit solution. So if there's a really particularly tricky, dog toy or something like that, we don't need to stow 100% of the inventory. We put some thresholds and we keep an exclusion list. So there are still people that are doing some of those hard items. And this is one of those, let robots do what robots are good at. Let people do those high dexterity tasks that are maybe still a bit in front of the state of the art for robotics today. So our eligibility at the moment is 70, 80% of the items. And that's actually very good. Fullness, so how much stuff can you fit? GCU is gross cubic utilization, so it's sort of volumetric fullness. Damage, we want to minimize the number of times we poke a hole in something or drop something. Amnesty is our word for, the item has left the bin. Either at your station you've dropped it on the floor, or you didn't get it into the bin, and so when that Kiva robot takes it away, somewhere as it's driving around it falls out. We call that amnesty. So this is our sort of marketing version of the video. I'll show you more, but what you can see from this one is that we have a robot arm that rides on a 7th and 8th axis. We have a horizontal vertical gantry. That's to grossly position the arm, either at the top row, bottom row, middle row. Then we have a second robot that sits in front of that system that's doing the elastic band manipulation. And that's a gantry robot. We have 3 degree of freedom and 4 degree of freedom versions of that. You also see our end of arm tool there, which enables the item to be conveyed into the grasp and then ejected into the bin without putting that gripper in. The bin manipulator, it's just an extendable piece of sheet metal. So a choice we made early on was to break the process into 2 steps. So we singulate the items first, and then we stow them. And that enables that conveyor feed into the gripper. We're not trying to pick the items out of a tote that might have 10 or 20 items in it. That's the singulation step. And this is kind of a philosophy lesson, I guess. I'll get on the soapbox for a moment. Trying to create a generalized, can do everything kind of manipulation is crazy hard, and you might have to wait too long for a system that can do all of that. But if you can narrow down the tasks, if you can control the environment, you can specialize your end-of-arm tool, specialize your grippers, you can control the lighting, the sensors more directly, and this will allow you to accomplish something earlier. So even though, yes, it would be desirable to have a single robot that could do it all, by making this split, we get something in 2 or 3 years as opposed to 20 years. And I think this is the same reason robotics did so well in manufacturing first, because that's the same task repetitive over and over and over again. So you can have a highly specialized end-of-arm tool that all it does is grip the windshield or the rear view mirror and put it in place. We're sort of extending that a bit. I talk about high clutter and high contact as the big challenges we're trying to solve. But it's not generalized manipulation. So here's what that looks like as a work cell design. We have a singulation step that's over here. This is shown with people. I'll show you some robots that can do this also. And they're fast enough doing that singulation, just taking the items out one by one, doing a barcode scan. They can feed 3 robots. So these people are going, 1,000 units per hour. The robots are a few hundred units per hour. It does allow you to mature these technologies independently. So as soon as we have a good singulation robot, we'll just drop it right in. And this is one of Amazon's singulation systems. It's called Sparrow. So it's a pick and place task. One of the cool things about this is all of those tags, all of those markers allow us to, on the fly, determine the pose of the object in the hand. Because we can calibrate off of those markers, and that enables you to pack much more densely. And so when you pick, you don't know what kind of pose you're going to get with that item, but you get it in flight, and then you adjust your packing algorithm so that you can try and fill up the totes it's going into quickly. For us, we don't really need that. We just need the items one by one singulated out. When you use suction cups to do that kind of picking, though, really good at certain things, like getting a credit card off the bottom of the bin. Not so good if you're trying to pick up a book. So if you lift a book, with a suction cup by the cover, it's going to flop open. Sort of a redeeming fact about humanity in my mind is we still sell so many books, 7-8%, something like that. Last I checked. So there's still some readers out there. There's also a lot of adult coloring books these days. We saw that go up, but. So what do you do with that? There's worse cases also. Maybe something's in a bag that's loose, and then you pick the bag, and the item stays behind. Or you pick a barcode sticker that's not, well attached. In the worst case, I actually saw it was kind of I'll show examples of this. It was kind of it wasn't Magic the Gathering, but it was this kind of like card game. And the robot picked the lid of the box and then dropped it, and then one by one picked 100 cards out of the box, and then picked the bottom of the box. And so you need a solution for these kind of things where you don't have a good surface for suction. So these are the failure modes. This is the blooper reel. You don't want to see your item getting handled like that, right? And so I have a team in Berlin, Germany, and so we did a project looking at two-fingered grasp, which of course is a nice complement. I don't think of it as an alternate. I think of it as a complement to suction. And it handles books, it handles these things. One of the big key, unlocks for this work was predicting empty space. So yes, we need a good 3D representation of the world, but for pinch grasp, we actually wanted to have good estimates of the occluded space that you knew you could put your finger, underneath the pile. And so we had sort of multi-view cameras, and we're doing like a signed distance function representation to try and predict this grasp poses. I'll let it finish. We got them all, so this was cherry-picked video, right? And this is going pretty fast as well, so this is over 1,000 units per hour to give you a sense of the speed. Okay, so that's the singulation step. And I'll zoom in a little bit more on the stowing robots for the rest of the talk. One of the things I learned at Stanford that's been most valuable for me is iterative design. We really embraced that in our work cell architecture and in our prototyping methods. So we started with really simple stuff. This is aluminum extrusion. This thing was cantilevered. It would wave back and forth by at like 1 or 2 hertz. We used Blender to really visualize the workspace. But the value of doing this kind of prototyping is that you really understand your problem a lot better. It also gave the motion planning and computer vision teams some early test beds to start development on. And we knew that we were going to iterate. And so once we got something that we liked, we built a hardened version. And this is in a fulfillment center. It's in a warehouse. That's a test warehouse. And so it's processing live orders. We get to exposure to all the variety of items and bin conditions and edge cases, but there's always kind of a backup plan. So inevitably the robot goes down for a day, if you're lucky, or a week, if it's tricky. It's not like 5,000 people don't get their birthday presents in Redwood City. And so we've been doing this for about a year. We've got 100,000 stows or something like that in this test environment. And then I'm very excited. We just launched in Spokane, Washington, at a live FC, a prototype of this that'll work through the Christmas season and give us real data. And it's, it's not a test environment anymore. This is our first foray into truly the real world. We also iterate, of course, on the pieces of the system, so the elastic band separation. One of the interesting failure modes, I don't know if any of you caught this in your head, when we open the bands and pull some of them down, we will trap sometimes an item against the floor of the bin. So imagine like a t-shirt in a bag. You may pin the bag on the floor of the bin. Now I try and sweep it to the side, and I'm fighting myself, or I'm ripping that bag open. And so we moved on, I don't know if this video, to more of a hook design, working on both the mechanical design of that as well as the motions. We do have force sensing in the loop on this, so we can plan those motions not just based on waypoints, but also based on contact and things like that. We continued this work, and I really wanted to show these videos because they were made by some of our interns. And so we had a pretty good success rate, but sometimes the top band would slip off. We also had this bin lip, the fabric lip along the bottom of that bookshelf. It's fairly stiff, and if you're trying to stow a tall item, you either have to twist the item to get around that bin lip or otherwise, deal with it. And so our interns set out to build better mechanical systems and build better motions. And this is what they came up with using, the UR robots as a test bed. And now we can fuse those into our work cell now that we have data that gives us confidence in their performance. We also have design iteration in the gripper itself. So we really followed kind of that IDEO brainstorming process. We went for volume. We spent, a good couple of weeks coming up with every concept we could think of, yes and, not no because. We filtered those through a set of criteria and prototyped 3 or 4 of them using, literally popsicle sticks and styrofoam and things. This was right peak pandemic. And so we were doing this sometimes in our home with, cereal boxes in the pantry. And once we got something we liked, we matured it. And so we picked this style, these 2 plates, and we call it a panini gripper. I hope that is obvious why. We liked that because you have 6-DoF pose control of the item. So if you have a 2-finger gripper and you've got a t-shirt, it's going to be flopping around. You're not able to control that precisely as you try and stow it. The other reason we really liked it is you have a known engineering surface that you're making contact with the world, which is the back of the paddle. So rather than trying to push, with a book on one stow and then push with a t-shirt on the next stow and then push with a teddy bear and then a bowling ball, we have this, at least one side of the contact is well modeled, well understood. And that evolved into a special bin manipulator, this piece of sheet metal. And in V1, that was kind of a fruit ninja, like it would rotate and chop down. And then it became more of like a Wolverine style where it would extend out from inside the hand. The latest thing we've done here is move the force torque sensor from the wrist out to that paddle so that we don't have all the inertia and losses of this end of arm tool that's a couple of kilograms. And that's actually really improved our control bandwidth. So here's what that looks like. Next steps, of course, also are some design for manufacturing, some cost engineering, things like that. One of the other things I'm proud of with this work is on the electrical side. So Amazon and most warehouse robotics, industrial robotics folks are using sort of system integration techniques. And so you have a big electrical cabinet with servo drives that cost 500% of what you think they should cost if you've taken 218. And you run all these cables that are way bigger and stiffer than you might need them to be. And so with 4 servo motors and force torque sensors and limit switches, I think we were up to 15 or 16 cables in this enormous fire hose-like dress pack. And as you're trying to do compliant control and you've got a 10-pound cable flopping around, I can tell you that generated a lot of noise that was affecting our ability to understand what was happening between the gripper and the items. So we built our own embedded board with some of those motor drivers. We're using EtherCAT as a protocol. So found some EtherCAT servo drivers, and now we have single connector, right? We're down to 5 conductors, I think, from 64 and 15 cables. So this is the other thing iteration gets you. If I shift kind of to the robotic science side of the problem, there's 2 primary areas I like to talk about. One is compliant control. So adding that force and torque in the loop signal, high bandwidth, a couple of 100 hertz in that control loop. And then the second is the decision making. So we definitely need a good 3D representation of the scene. So the computer vision piece is foundational, but that's not enough. So it's not a peg and hole problem because the hole is not always there. We have to create the hole. And so you have to reason over that 3D representation of the scene and predict where you might be able to make space if you were to do some of these motions. So you have to create the hole, and then your peg is shaped like an Amazon item, which again is teddy bear and then bowling ball and then USB stick. So I'll talk about each of these. We have other science, robotic science, that we leverage. So a lot of free space motion planning. But here we're not really trying to invent. We're trying to capture what's already state of the art. And so we do Como formulations for our free space motion planning, which is from Mark Toussaint over in TU Berlin. We've also done some of the techniques that Russ Tedrake out at MIT has put forward. We are also running always kind of a recovery plan so that when we don't make enough room and we think we can sweep 10 centimeters, but we were wrong and we only get 6 and the item in our hand is too big, we want to have an immediate way to recycle that item. So at Amazon, those seconds count. And so having to wait there to recalculate, your recovery trajectory costs a lot of money. When we think about the first science challenge, where I would say we're doing some of this invention, that force and torque in the loop control, we've experimented with impedance style controllers with torque sensing at each joint, torque control at each joint in the robot arm. And we've also played around with admittance controllers, where we are only using the force torque sensing at the wrist or even now further out at the blade. And we landed on the admittance side of this classic debate because the contact is always occurring through that blade. It's never the case in our application where the elbow of the robot is getting into contact, nor are we able to generate kind of a good model. So our impedance controllers would fail because we would pick up an item that would have sort of unknown or not well-modeled mass properties, and then we weren't able to kind of keep a good model of the robot updated. So I think in the long run, it's maybe more ideal, but we found the admittance control was really practical and viable for our application. Another simplification that made this a tractable problem was not trying to imagine any motion under the sun. We have canonical motion primitives, and so it collapses to a problem of picking which primitive and which initial conditions to use, as opposed to trying to come up with a new strategy on every bin. And so we have these 4 primitives. Slot wedge really is the peg and hole problem. There's empty space or it's an empty bin. Just go chuck an item into that bin. Stacking is sort of similar. You have an empty space, but we are reasoning about the stability of that pile using surface normals to decide whether or not it's going to stay there or fall out later. Bin sweeps are probably the most common. Here you might have a stack of library books that has fallen over, or a bunch of discrete items with spaces in between. We insert that sheet metal blade and then push everything to the side to consolidate the available space, even compressing sometimes those items that are t-shirts or other things that are not harmed by being squeezed. Probably the most fun is flip up. So here's where a book has fallen over flat in the bin. You don't want to create a pile. That actually makes it harder for the people that have to pick the items out. If you're trying to get the book off the bottom of the pile, it's way worse than getting the book out of the middle of the library shelf. And so we put that blade underneath the item and then rotate it up to the side. And there are sort of variants of these. It's more of a spectrum than really 4 discrete points, but I'll show you videos. So here's slot wedge. Again, this is the easiest, empty bin or empty space. Take the item and put it in. In fact, now we make a calculation about whether we even need to extend that sheet metal blade. If it's an empty bin, just aim for the middle and go as fast as you can. For stacking, we have methods where we actually use that blade to push down the elastic bands so that the pile won't fall out, or we have a lower probability of the item that we're putting in the bin to fall out. But we're essentially inserting things on top. What I'm not showing is some of the surface normal calculations that we've done recently. This is kind of an ugly pile. We generally would not want to stack an entire bin. We'd want to put one item on top, only when it's very dense. This is actually a knob that they turn on and off in operation. So during the 9 months of the year before now, they will ban stacking. They'll tell all the people, like, don't stack any items. And when we get ready for the holiday rush, they're like, any way possible, get those bins as full as you can. So from a robotic perspective, we can also turn that on and off depending on conditions. OK, so here are bin sweeps. And this is sort of interesting because there's more steps in the process. So we're indexing. We touch the item there to index off of before moving to the wall of the bookshelf to do the full blade insertion. And that takes out some of the error. Your perception system might have 1 or 2 centimeters of stacked up error. And so that's too much to have a high reliability blade insertion in these dense bins. And so we'll do the same thing a human does when they're picking up a coin off of a table. Rather than trying to go precisely to the spot in space where you can grasp that coin, you go to a reference, make contact, and then slide along that contact until you can accomplish the task. You'll see different strategies here. Sometimes we're inserting the blade above the items and kind of sweeping down. Sometimes we're seeking out that wall, that's the fabric wall. And sometimes we are just going into empty space where we have confidence that there's not going to be a collision of the blade. You can see this is with the old gripper. If you look closely, there's this nasty bundle of cables that are on the back. And one of the other interesting things, I think, from a science perspective that we're doing is when we stow to the same bin multiple times, we use memory. So we know how much space we were able to create when we did the sweep. And so you can use that rather than your perception output, because you have now a ground truth measurement. You can use that to update the bin item match as well as the kinds of motion primitives that you might use. So here's flip up. We're also, again, trying to make these fast, and so that's a challenge. That's why you want that really clean force torque signal, because you don't want to sit there and filter it for a long time. Yeah, okay, so I'm going to switch over to the other science problem now, which is the decision making. And so the seed of that is the computer vision. Here we also took an iterative approach. So it's the same principles whether you're in hardware or software. We started with something simple, which is an occupancy map. Basically, it's a yellow, not yellow model, right? When the bookshelf is all yellow, that's what it's learning. We also had a elastic band segmentation mask, so we know where to put in that hook to lift the elastic bands out of the way. We evolved this pretty quickly. And so the logical next step, of course, is segmentation. And we've actually got instance segmentation. We're actually labeling the items now. Sometimes we're able to tell which item it is based on dimensions or color, RGB embeddings, that kind of thing. And so we will use that to determine whether we can compress the stack or not, for instance. We would really love to have some depth information. That would help you. We are confounded by those elastic bands. So the traditional techniques, you say, just use a LiDAR, projected light, pattern. These don't work well at all because you get all these false returns from the elastic bands. And so what our team is doing instead is trying to infer depth from monocular images. So the problem is fairly structured. We can collect ground truth data with those kind of LiDARs and other sensors, active sensors, when the bands are removed. And then compare them to the 2D images we have, and because of the structure of the problem, we can actually get a fairly good inferred depth model. We can also use simulation, so that's what's shown here. That gives you ground truth really easily, lets you build up a backbone of your model, and then you augment it with some real data from the field. The other thing we do to deal with those elastic bands, we have something called blind in-painting. So some of your cell phones have this. If you have someone who's photobombed you, you can kind of magic eraser them out. Same techniques here to hallucinate the pixels behind the elastic bands. And if we do this as a pre-processing step before the segmentation, we do get better results. Again, works pretty well because our domain is fairly well defined. So this is, again, that difference between a general, works everywhere in the wild problem and, how to structure your system so automation will have a good chance. Yaw and perspective, this was the one that surprised me. I sort of thought we would be able to geometrically handle this, but it turns out it's a lot harder than we initially thought. It's challenging because both the floor of the bin and the wall of the bin are that same yellow fabric. So your camera has a hard time determining, especially when that floor might have a curvature because it's fabric. The other problem here is the item might be pushed all the way back against the back of the bin, or it may be way up at the front. And if you have a box, it could be sitting perfectly square, or it could be yawed. And so in your 2D image, you may have some bin that looks like it's completely full. Your manifest says, it should be a quarter full, and it's because that item is rotated in the bin. And so we've done a lot of work to try and correct for that perspective error, and sort of do orthographic reprojection to accommodate the angle that you're looking out at the edges of the outer bins. So this is still work in progress, but for the computer vision folks in the room, if you have ideas, this is my solicitation. Another improvement we made was labeling every pixel in the scene. And some of this is useful, like that bin lip, understanding where that bin lip is. You can change your strategy. Also, we have these metal bars that are the frame of the pod. And obviously, you get a different response if you sweep your piece of your bin manipulator into the metal bar than you do if you are pushing a t-shirt. And so knowing where those are also gives us better performance. And so this was a step up. And now we've moved on to inferred depth from stereo, which I know sounds a little weird because you generally think you're going to do dense stereo geometrically, but we're actually taking the stereo as inputs and then training a model, again, using that ground truth depth sensing because of the elastic bands. So when we try to make a decision about which of the 30 or 40 items that are available to us should go into which of the 25 or 30 bins are on the bookshelf in front of us, we currently have sort of a decision tree that some of those leafs have a little bit of ML in them, but it's at the highest level, it's kind of a one-size-fits-all. So we're not adjusting that model for when we have a 1-pound item versus a 1-ounce item versus a 5-pound item. We're not adjusting it for when the bin is super full versus pretty empty. And so we've engaged in some work with a professor from University of Washington, Lillian Ratliff, who's on sabbatical with us, to try and model risk so that we can have more tailored motions depending on the bin state and depending on the item that we're stowing. The other thing that we like to do as a good example of the value of this work is you might want to stow the first 6 items that you can fit into the bin face using a fairly conservative set of rules. But when you're ready to kick out that pod, when you say, I can't stow anymore, that's the time when you should take risk, right? That's the time when you might want to say, well, I have 88% confidence or 92% confidence in this stow. Now you can do an assessment of the time penalty it's going to cost if you fail versus the extra stow, the value you get from that. And so Lillian's working on this. It's super exciting. So this is sort of my penultimate slide. What I hope you take away from the talk today, besides the, oh, cool, like that's a fun robotics application. I hope you do take that away. It's super fun. Way more fun than I thought it was going to be actually when I made that leap from the volcano robots into warehouse robots. But the other thing I hope you leave with is an understanding of some of the problems that we face in industrial robotics as we try and take research results from the lab and apply them in a business setting. And so I tried to list some of the problems we face, and I hope maybe some of you can see how your research here fits into some of these domains and might provide answers to the problems we have now and with the next applications. Of course, we also have job opportunities for bright Stanford graduates and folks looking for internships. So there is a jobs website. If you look for Amazon Robotics, there's a bunch of posts there. I'd also just encourage you to connect with me on LinkedIn, and I can direct you to whichever's the appropriate place for you. I have saved time for questions, and so I'm excited to hear what you think.
Hi, great talk. It seemed like a lot of the problems that you were dealing with are also related to the bands in front of the things, right? So I know this is a huge scale operation, and those bins are maybe throughout the world, but was there ever the option to question whether you could change the bins themselves to make your whole robotics problem easier and give a bigger picture at the end?
Yeah, which is the philosophy I was kind of espousing, right? Yeah, we did consider that, and you're right, the scale of this is enormous. So in the world, I think there's around 5 million of those bookshelves. So not only is it the cost, but it's also the logistics and the labor to change them all. In Amazon, we talk about green fields and brown fields. I think that's actually pretty common terminology out in the warehousing world. And so it's much easier if you're talking about a new building, a greenfield building, to consider other architectures. My team has been pretty focused, and I try to drive them to stay on this target of surgical retrofits. So we already have 100 buildings, right, or 150 buildings. They exist. Try and live in the world that already exists. There's a different project at Amazon. You can look it up where they're looking at containerized storage. So you'll see a lot of systems out there, often referred to as ASRS, Automated Storage and Retrieval Systems. We basically have tubs that are moving around. And so rather than having vertical shelves, which is sort of a challenge for robotics, you have a bin so that gravity is working in your favor. So there's a project at Amazon that's already pushing on that domain. And so we really are trying not to change the world that exists. The other thing is, like, in the big Amazon ecosystem that I showed you in that initial video, it is 20 processes in the building. And so when you start changing things, those can have unintended consequences upstream and downstream. And so, for instance, our quality control is trained on the thing that exists. And so if you change it, you're changing their domain as well. But yeah, it was a hard discussion that we had. Yeah.
Thank you so much for the great talk. So you talked about the computer vision problem where you were having issues estimating the depth. So what you were doing basically was capturing stereo images, getting the disparity image, and then calculating the depth, right?
Mm-hmm.
So why don't you use any dynamic volume rendering technique like neural radiance fields? So basically for each and every compartment, there is a simple multi-layer perceptron which is really easy to compress, and it is computationally very inexpensive. So every time something gets stored into that shelf, the corresponding model will get updated, and it is very easy to estimate depth information out of neural radiance fields. So why don't you think this is a added?
Yeah, it's a good question, good line of thinking. So thank you for that. We have what we call a coarse update and a fine update in the stack. And so when the pod shows up initially, we're imaging everything, right? And we haven't lifted the elastic bands yet. And so the elastic bands are really what kind of degrade the performance of that like disparity matching technique. And that's why we use the inferred depth. It's in that coarse update. We do capture images whenever we lift up the elastic bands, and that gives you this better view. And so we do what we call a fine update, and that uses some other techniques to try and refine the state of the bin. So I don't think that's a perfect answer to your question. Like, you could still ask, well, why don't we use that strategy in the beginning? And all I can tell you is, like, we are trying these things, and so far this is the best performance that we've been able to get. Yeah.
My question is, like, when you're putting things in versus putting things out, why are you like making specific hardware solutions for one and the other? Because if you made the hardware the same, like, I know it's difficult, I'm assuming, to like make sure that it's going to be the same, but if you made it general and then you like basically sent the problem to the code effectively, would that be easier?
Easier for the hardware engineers. Yeah, so we looked at this too, of course, and we did a big analysis that Amazon will actually flex some of the stations back and forth between pick and stow, depending. October, we're doing a lot of stowing. Black Friday, December, we're doing a lot of picking, right? So the fullness of the bins will ramp up, and then as people start doing their holiday shopping, it'll be a steady decline. It just turned out to be too difficult from the manipulation tasks. So for stowing, we like to have that pose control of the item. For picking, that's not important. If the item dangles, it's okay. For stowing, we're feeding that item in with the conveyor belts. It'd be pretty difficult to get the item essentially started. So we'd need some kind of suction system or some kind of gripper to get that started. We are trying to share as much of the hardware as we can, and so the 7th, 8th axis gantry, the band separation, some of the software interfaces as well to like accept the pods and send them out and log into the stations. All of that stuff is shared, but we are strategic about when it's easier and when it's sort of harder, and kind of fell into that general manipulation category. It was kind of too hard for us to make it the same. Yeah. Yeah.
Case of objects falling out of the pod, say the gripper drops.
It's not that rare.
It's not that rare? Okay. Say the gripper drops the object, or when you move the elastic band, because of the orientation, the object falls off.
Yeah.
Does the system know? And second, what happens?
Yeah. So sometimes the system knows. So we do have an overhead camera, and we have an amnesty detection model, and we have an overhang model, which is like an amnesty risk model. And so if we detect the item and we can tell which item it was, then we'll autonomously heal the system, right? And we'll just make sure that the inventory record is clean. And then once a day, a person will come around and pick up the 10 items that are on the floor and put them back if they're not damaged. There are cases, though, where you don't know, or you don't know which item it is. And this happens with people as well. And so there's already an established quality control process in place that, it's called a pick short. Basically, it'll come to a station and say, pick the iPad, and you're looking, and you're like, there's no iPad in this bin. And then it knows that there's a defect, and maybe somebody found an iPad out on the floor, and they're like, oh, these two go together, right? So there's a bunch of systems like that to deal with the edge cases. I say it's not that rare because, again, something like 10 million picks per day, right? So we get a lot of it. Yeah, other questions? Sure.
Do you have trouble with people picking yellow or reflective items?
We don't have trouble with people picking those items. We do have trouble, of course our segmentation model is not perfect. So yellow items are one flavor of error. Reflective items or dark items also, classically cause challenges sometimes. So we have errors in our segmentation masks that are based on that. On the pick side, the errors we have are when you have items that look very similar to one another, or we also have models that are trying to tell if items are occluding other items. So you don't try and pick an item that's behind one and then pull out the item that's blocking it. So there is a bunch of those kinds of cases that do exist, yes. And that's kind of the long tail of going from proof of concept to product. Yeah?
You mentioned that movement control requires a model of what you're picking. Have you looked at online system identification or learning?
Yes. Yes, we have. And so we did do some of that and then tried to update our models, and I would say mixed results. I think that, I think you could make that technique work, and it was just that the admittance control felt like an easier path, or the data told us it was an easier path at the time that we were doing that exploration. And so, we were putting chirp signals and trying to build up that model, and we're making progress, right? That's the right way to attack that problem. But I think it got cut short a little bit. It's not a dead end. It was just a harder path. Yeah, go ahead.
And did you investigate RL or education or anything for this, since people
Yeah.
in academia are looking at it a lot?
So, we had some of our interns, as it turns out, investigate some of those techniques for us. I like to use our interns to sort of get one step ahead of the team and triage. Is there juice in this orange, or is it dry? With the reliability we were trying to get to, RL was not sufficiently performant at that time. This was last 18 months ago summer that we really investigated it. Going once.
Any more questions?
Yeah.
Maybe we'll break here. Let's hear it again for our speaker.